Hello, everyone, and welcome. My name is Jessica Williams, and I am the Programs and Community Partnerships Manager at Chabot Space and Science Center. And we are thrilled to bring you another exciting program live to your homes this evening in partnership with the SETI Institute. Tonight, we have with us Dr. Simon Steele, and he will be taking us on a luxury cruise to the center of the Virgo Cluster. Dr. Simon Steele is not only a galactic cruise director, he is also the director of education and public outreach at the SETI Institute in Mountain View, California. As an astronomer, he studied distant galaxies, but spends more time these days thinking about aliens and the search for life in our own Milky Way. He will also take questions from the audience at the end of Dr. Steele's talk. So please be sure to keep your questions and post your questions in the chat for us at the end. Thank you, Dr. Steele, for being with us today. It's such a pleasure to have you.
It's great to be here. Happy New Year, rather belated now, as we're well into 2021 to everybody. So yes, welcome. This is actually the 6th of the joint SETI Institute Chabot Space and Science Center talks for families. All of the previous ones, of course, were in 2020, and we're hoping that in 2021 we will continue with this season and bring you talks about the universe from lots of different scientists and astronomers from the SETI Institute and beyond. Some of you may have joined me on our little cruise to the center of the Milky Way last year. And you may also remember, and a lot of you know, that the Milky Way is a galaxy. It's a city of stars. And I have here a scale model, which will become very useful to us as we take our tour outside the Milky Way. This is a CD. Which again is rather ancient technology. And in the middle, I've popped a little sort of a fluffy bit of cotton wool there, which is an indicator of the central bulge of our Milky Way galaxy. The dimensions of a CD actually are very conveniently similar to the dimensions of a spiral galaxy that the Milky Way is. It tends to be very thin and a big disk of stars that rotates around every 200 million years or so. The sun and the Earth and the solar system is about sort of halfway out in one of the spiral arms. We took a journey to the center of the Milky Way and saw the giant black hole at the core of our galaxy. But I think that was just a tour of our little local village, and it's time to go downtown to Galactic Central Park, Galactic Times Square, and that is the Virgo Cluster. So I'm going to put this CD down, and I'm going to start the presentation now with the slides here. If I can find the share screen, there we go. Now let's start actually, ignore the rocket ship in the corner. That's what we're going to be traveling on. This is an image of the night sky looking up in, it's probably if you went out around sort of 4-ish in the morning, this will be the view looking sort of south. And some of the constellations may be familiar to you. I'm going to use the mouse to point out some familiar constellations. Here is the Big Dipper. And here's the handle of the Big Dipper going down to a bright star Arcturus. And down here is the constellation Virgo, and to add in a lovely little graphic showing where Virgo is, ignore Vesta, that's an asteroid, that's even closer. Virgo is a collection of stars that humans have made patterns and stories of. Virgo is one of the 12 constellations that are in the zodiac. These are constellations that are special because they align with the plane of our solar system. And so the stars, or rather the planets and the sun and the moon, all orbit the sun and go through these 12 constellations that form the zodiac. Zodiac is a derivation of the word zoo, or same root as zoo, and it originally means circle of animals. And most of the signs of the zodiac are animals, but then there's some other things like scales and people, as in Virgo. So this part of the sky, the stars that we see are actually local. They're very close to us. They're all Milky Way stars. And we have to look through those stars with very large telescopes. And behind those stars, we look out into intergalactic space, and that's where we're going to be traveling today. So we're actually, although it's called the Virgo Cluster, which is a cluster of galaxies, it's nothing really to do with the stars in the constellation of Virgo. It just happens to be, if you look in the direction of the constellation Virgo, you look through the stars of our galaxy out into the depth of space, and that's where we're going to be traveling. So everyone needs to get on board our spacecraft, and we'll get going and get into orbit. Here, as we jump up, we'll get a nice view of our Milky Way, our galaxy. Here's the Earth. We're just orbit out of the way of the Earth and get that moved for now. And what we see now is the plane of our galaxy. Of course, we're looking, the galaxy is in the shape of a CD. We're looking through the galaxy. We're looking at the plane of the galaxy. And here we're looking towards Sagittarius, another of the zodiac signs, towards the center of our Milky Way. And you can see, well, you can't see because there's all this stuff in the way, all these little dots are stars, of course, but then you have these huge dark dust lanes, and then a few little pink patches. The dust is the interstellar medium, the stuff between the stars, and this is the raw materials for making new stars. And as that dust and gas collapses under gravity, it heats up and then ignites with nuclear fusion and starts to radiate as stars. And the pink regions you see are glowing bits of hydrogen gas, and those are the indicators where the new stars are being formed. So this is our galaxy. These are the characteristics of a spiral galaxy. Lots of stars, lots of new stars being made, and lots of gas and dust sitting in this big disk in which we live. If you look slightly to the bottom right, you'll see two other fuzzy blobs. There's a big one and a small one. These are called the Clouds of Magellan. They were first discovered by Ferdinand Magellan, who was one of the first navigators to circumnavigate the globe. And in the southern hemisphere, you can see these two clouds. The Greek word for cloud is nebulum. So these are nebulae, but they're actually galaxies. They're called the Large Magellanic Cloud and the Small Magellanic Cloud. I'll leave you to guess which one's which. But we're going to stop off visiting there first as we work our way out of our Milky Way. But first of all, I just want to come back to our nice model of our galaxy. There's our Milky Way. There's an indication of where the sun is. Now, we don't know what the Milky Way looks like from the outside because the furthest we can get is just barely outside our solar system. And the Milky Way is huge. It's 100,000 light years in diameter. What does that mean? Well, even if you travel at the speed of light, it's going to take you 100,000 years to get from one side to the other. Our journey to the center of the Milky Way was a journey of 26,000 light years. So even at the speed of light, it would have taken us 20,000 years to get to the center. Now, so, you know, there's accurate science in this talk, but as far as our ability to travel this fast, you know, maybe we're pushing the limits a little bit. But let's compare our galaxy with a CD, because we're going to use this to get an idea of how big the distances are we are traveling. Now, a CD is about 5 inches across, 12 centimeters. I'll put this in metric and in old-fashioned Anglo-Saxon units, as they're called, the inches and feet. 12 centimeters is about 5 inches. We're going to be roughly rounding these things off. And so if we're using this CD as a scale model for the galaxy, it means that every inch across that CD is 20,000 light years. And so in order to get an idea of distance, we're actually going to, as we travel out towards the Virgo cluster, we're actually going to build a scale model, which is something you can do. If you've got a few CDs lying around, you can build a scale model of our local supercluster of galaxies. So this gives an idea of scale. And when we look at distances in terms of light years, we'll also bring up the distances in terms of CDs as you can build your local neighborhood model of intergalactic space. Now, light year as a distance, it sounds like it's good years. It means that that's the distance that light travels in 1 year. And light travels very, very quickly, 300,000 kilometers per second. But even at this huge speed, it still takes 100,000 years to get across one galaxy. So we're talking huge distances here. But anyway, enough of this. We need to actually move out of the galaxy. Actually, as we head out the galaxy, what we notice is our galaxy is surrounded by lots of things. It's not in isolation. There's an object that we're going to go past called Messier 4 as we head out. Messier 4 is what's called a globular cluster. A globular cluster is a big ball of stars. They tend to be very old stars in most globular clusters. They were formed a long, long time ago. It's about 100,000 to a million stars in a globular cluster, and our Milky Way galaxy has about 100 or so of these things in orbit, orbiting around the center of our galaxy, like bees around a honeypot. Messier 4, and we'll see that word again, Messier. Messier, Charles Messier was a French astronomer. He used to love comets, and when he looked up at the sky in the 18th century to search for his comet, he kept seeing these blobs, these nebulae, and he got fed up with them. He kept thinking he'd discovered a comet, but no, he didn't. And so what he did was he labeled all of these irritating blobs in the sky so he wouldn't get them messed up with comets. And they were called Messier 1, Messier 2, as he discovered, and it goes up to 104. What's very interesting is that all of these blobs that were just irritating to him turned out to be some of the most interesting objects in the universe, and we are going to pass a lot of these Messier objects, but that's the origin of this term. These globular clusters aren't far, they're 7,000 light years away, which is, that's nothing really. In our model, that's about a centimeter or a third of an inch. So you can imagine these globular clusters on our scale of our CD, a little tiny balls, maybe sizes of sesame seeds, scattered around our little CD, very, very close by. We haven't even reached our nearest galaxy. Nearest galaxy turns out to be these two little dwarf galaxies, they're called. They're very small, about a tenth of the mass of the Milky Way, and they're in orbit around our giant spiral galaxy. So let's take a quick visit to these little galaxies. This is the small Magellanic Cloud close up. You can see from here that we can actually, all this what looks like a fuzzy, messy, noisy image is in fact all of these little dots are stars as we fly past here. There's a nice round blob to the upper right, and that is another of these globular clusters. That's only about 10,000 light years away, so that's a tiny distance. That's a foreground object compared to the small Magellanic Cloud, which is 20,000 light years distance. So the light from the small Magellanic Cloud takes, sorry, not 20, 200,000, takes 200,000 years to get to us. It's about twice the diameter of the Milky Way away from us. On our scale model, that's around 10 inches away in our scale model as we build it. And you can imagine the small Magellanic Cloud, which looks a bit messy. It's a bit distorted. It may have had it look like a mini spiral in the past, but it's so close to our Milky Way galaxy that it's really got distorted, what's called tidal distortion. The gravity from our giant galaxy has messed up the shape of this little galaxy. And that's a theme that we'll see throughout this voyage is gravity rules almost in everything that we look at. And getting too close to a big galaxy is not a very good thing. And the small Magellanic Cloud is distorted because of that. Let's move on to the sibling as we whiz around. The large Magellanic Cloud, as the name suggests, is slightly bigger. And as we look around here, it's a similar distance away from the Milky Way, and it's locked in a little dance with its smaller sibling, and it too is very, very badly warped, and you can see possibly a line of stars across the center running diagonally that may have been a bar or a disk of stars, maybe a little spiral structure, but it's a bit of a mess at the moment. They're called dwarf galaxies because they're quite small, and they're called irregular galaxies. As we'll see as we go out, we'll see different types of galaxies. Spirals, yes, we've seen, and irregulars like the Large Magellanic Cloud. You can see different colors here of stars. Some stars are blue, some stars are mixed together and sort of yellowy like the sun. And again, here are these pink blobs that are very, very hot ionized hydrogen, and they're glowing like fluorescent tubes because of newborn stars. So there's a lot of newborn stars going on in our neighbor galaxy, the Large Magellanic Cloud. And in fact, quite coincidentally, the biggest star birth factory that we know of in the universe is actually in the Large Magellanic Cloud. And if you look at a pink region just above the yellow collection of stars, this here, we're going to zoom in on this now to take a quick peek at this region. So let's zoom in, and we suddenly see that this is a huge tangled mess of red hot gas, hydrogen gas, filaments everywhere. This is called the Tarantula Nebula, which is this is the biggest tarantula in the universe. You know, we're getting to see some big, strange animals, and this is probably the strangest here as we fly through the universe. The Tarantula Nebula is this huge star factory producing hundreds of thousands of stars. And it's thought that as these stars are born, and when they're born, the winds from these stars will blow away all the leftover gas. What you'll probably end up with is a globular cluster, like that Messier 4 we saw. But this is a very new system here, and this is still going through the star formation process. The filaments, of course, it's all tangled because there's so much going on. A lot of the biggest stars that are made don't last very long. The more massive the star, the brighter it is, but the shorter its lifetime. So the sun is a mid-range mass star. It's going to last for about 10 billion years. But some of the stars at the center of the Tarantula Nebula are huge. They're 100 times the mass of the sun, 200 times the mass of the sun, and they're going to barely last a couple of million years. That's not long to long time to humans, but it's not long in the terms of the lifetime of a galaxy. So what we're going to do is just zoom into the center of this Tarantula Nebula. I don't want to get too close because this gets a bit nasty as we get into this central region. And as we zoom in, we can see the very heart of the tarantula. And this is a collection of incredibly bright, hot stars. And the biggest stars in this region at the Tarantula Nebula are thought to be about 250 times the mass of the sun, which means they are about 6 million times as bright as the sun. So you imagine this wonderful sort of jeweled collection of stars, all of them 1 million times brighter than our sun. And if this Tarantula Nebula were in our own galaxy, as close as our closest star-forming region, which is the Orion Nebula, that you can just about see with your unaided eye, it would be so big and so bright, it would actually cast shadows at night. It would be a very, very bright, huge, huge object in our sky. Not near us, it's actually in the LMC, Large Magellanic Cloud, and nothing to do with our galaxy. But actually probably something to do with our galaxy is the distortion of the Large Magellanic Cloud being so close to our Milky Way that's triggered this whole star formation episode in it. This is our local situation. The Milky Way has a few small galaxies very close by. These two Magellanic Clouds are the brightest and most famous. But let's move on to our biggest neighbor next, and that is a big spiral galaxy just like ours. This is Messier 31. It's the 31st nebula in the catalogue of Charles Messier. It's called the Andromeda Galaxy. It's in the constellation of Andromeda, so we've drifted away now to another part of the sky. The Andromeda Galaxy is 2.5 million light years away. 2.5 million light years means that light has traveled 2.5 million years to reach us from the stars in this galaxy. On our scale, that's about 3 meters or 10 feet away. So if you want to build your scale model of our local universe, you've got a CD representing the Milky Way and another CD representing the Andromeda Galaxy. And you put them about 10 feet apart, and that gives you an idea of the relative spacings of these galaxies. This is not how it would look if we were flying to it, because what you see is all these speckles of stars in the way. Those are all stars from our local Milky Way. It's like looking out of a car window, and the stars are like the raindrops on the windshield. So what you really want to do to get an idea of what a galaxy looks like is to take away those stars and see the galaxies as they appear in intergalactic space. So as we leave our Milky Way, galaxies are indeed just floating in this void. There is stuff there, but most of the mass of the universe is in these giant collections of stars that we call galaxies. They're referred to as cities of stars, and that's indeed what they are. Then the Andromeda Galaxy is a similar size, and you can see it has two very, very nice little orbiting satellite galaxies as well. As we fly through and past Andromeda, we get a vision of Andromeda that's very, very similar to the vision of our Milky Way. You can see there that each one of, again, it looks like a sort of messy, grainy image, but each one of those grains are stars. A lot of the brighter stars have these very long streaks on them, and that's because of they're a bit overexposed, and that's messed up the light a bit. But those aren't real; those are artifacts of this view. But you can see the big bright large dark dust lanes, just like we have in the Milky Way. You can see the red pinkish glows of the star-forming regions that are like the Tarantula Nebula, only smaller. It's a bigger galaxy, but it's got smaller star-forming regions. Some of the stars are pink, sort of yellowy, which suggests they're older and lower mass, and some of the stars are bluer, which are meaning they're hotter and therefore a higher mass and therefore have a shorter lifetime. So that's a view of the Andromeda Galaxy, and the Andromeda Galaxy and the Milky Way form what's called the local group. And just to have a look at where we are, it's always good to pull out a map sometimes when you're journeying to places you haven't been before. And we can have a look at what's called our local group of galaxies. And you can see that the two biggest members of the local group are our Milky Way here and our Andromeda Galaxy here, 2.5 million light years away. This is the distance we've traveled already, 2.5 million light years in 24 minutes. That's not bad going. You know, good job we got some good fuel supply left. You can see that the Andromeda is not the only galaxy. There's a ton of galaxies. These are all little smaller, what are called dwarf galaxies. There's another nice spiral, quite a sort of smallish one, called the Triangulum Galaxy. But these are a local group of galaxies, and these are the dominant galaxies in our part of the neighborhood. Gravity not only makes galaxies, but it also attracts them. The Andromeda Galaxy and the Milky Way are moving towards each other, and it's quite possible in about 4 billion years' time they'll actually collide. So we don't have to worry about it just yet. But in 4 billion years, when the Earth will still be around and the Sun will still be around, the Andromeda Galaxy will be a much, much more impressive thing in the sky, maybe too impressive, as these two galaxies are drawn together through their mutual gravity. That's the local group, but we need to get away from here because we're not interested in just going down to the local store. We want to head down to the city center, and that's the Virgo Cluster. So let's move out of the local group, and we'll start really heading into large distances of intergalactic space. Before we get to the Virgo Cluster, there's something we have to stop off just to have a look at on the way. It's a galaxy that we really don't want to go past, and it's called Messier 104. This is the 104th object in Charles Messier's catalog, and it's one of my favorites. And as you can see as we pass by, this is another what looks at first sight to be another spiral galaxy, like Andromeda or like the Milky Way, but it has this huge bulge in the center and this very, very clear ring of dust. It's very well organized, this galaxy, a lovely sort of perfect structure. What's interesting is that you can see we can see through this galaxy. We can see through to the other side, and here are a couple of long streaks, if you can see my mouse moving, of galaxies that are actually further away in the background. And we can see through the bright fuzz, and that bright fuzz is all the stars, the 100 billion or so stars that make up the galaxy M104. We can put on some, this is how M104 looks like in visible light, but maybe we can get a little bit of a different look at M104. So everyone needs to put on their infrared goggles now as you look out the side of the window of the spacecraft. And if we put on our infrared goggles, we can get a view that looks very, very different from the visible image. Here we can see infrared light shows what's warm. And we can see that this dust ring that's as big as the galaxy, circling a very, very a dense nucleus, is very, very clear indeed. A beautiful ring, not really spiral arms that we can see in spiral galaxies that we're going to visit, but a very, very distinct ring. And in the center of this galaxy, just like in the center of the Milky Way, just like in the center of Andromeda, is a giant black hole. And we'd like to stay a bit longer, but we're going to move on. How do we know there's a black hole? Well, actually, there's lots of black holes in this image. The trouble is it's very difficult to see black holes because they tend to be black. And the only way we can actually see them is if they have an influence on other things. They get an influence on other things because black holes have very intense gravity and they can draw material onto their surfaces. And as that material falls into the black hole, it gets hotter and hotter and hotter, gets millions of degrees as it falls into a black hole. And that hot gas, as it falls into the black hole, gives off X-rays. So we're going to put on our X-ray goggles now and look at M104. And if we look at M104 using X-ray light instead of visible light, we get this view here. And suddenly we have all these blobs. They look like Christmas tree lights. But what these blobs are black holes. We can't see the black holes, but what we can see is black holes that are in orbit, very close orbit to a neighboring star. They're called X-ray binaries. They're binaries. One is an X star, it's now a black hole, and one is a star that is going through its regular life cycle of glowing. But the outer part of the star is being torn off and being drawn into the black hole. And as that gas falls into the black hole, it gets hotter and hotter and hotter and glows in X-ray light. And you can see here hundreds of black holes that are suddenly revealed in this galaxy. And that's true for the Milky Way as well. You have lots and lots of black holes like that. We need to move on from M104. It's such a beautiful galaxy. We need to move on towards the Virgo cluster. Let's have a quick look out the window and have a look at the Virgo cluster as we approach it. And here it is. Now, a lot of the little dots are just stars, but anything that doesn't look like a star, that's not a dot, is a galaxy. The Virgo cluster here is made up of possibly 2,000 galaxies. Some of them bigger, some of them smaller, and they're all clustered together through gravity. And in fact, the gravity is so intense from all of these galaxies, from these 2,000 galaxies, that the Milky Way and Andromeda also under the influence of the Virgo cluster and are being pulled towards the Virgo cluster due to the gravity. How far away are these galaxies? Well, some of them are a bit closer, some of them further, but on average, they're about 54 million light years from us, from Earth. That means that light from these galaxies has traveled 54 million years to be gathered up by the telescopes on Earth. And in terms of our scale model, CD, that's 65 meters or 200 feet distant on the scale. So this is a huge distance that we have to travel, 54 million light years. There's lots of galaxies here. We're going to visit a few of them. We're going to visit a whole bunch up here in this region, but we're going to end up with the treat, the star of the show, which is the galaxy, the big one, slightly lower down in the center of the image, and that's Messier 87. Yes, that's another Messier object. Let's go in and have a look and see what's happening in here. And we're going to pass a couple of spiral galaxies first of all, because there's some galaxies in here that look very, very strange, and we're going to have a closer look at those. But first look as we pass in and travel into the Virgo cluster is Messier 61. Looks a very, very nice ordinary spiral galaxy. It's wonderful. It makes you almost sort of feel homesick for the Milky Way. It's face on. We're looking at this as a CD, face on. And you can see all the characteristics that the Milky Way has. It has a nucleus, it has these lovely big broad spiral arms. You can see the bright dust lanes made up of this very fine dust, sort of silicates like soot and sand, graphites and silicates that will collapse along with the hydrogen gas between the stars to form new generations of stars. You can see the pink regions, which are the star-forming regions, like the Tarantula Nebula that we saw, but again, not quite as big. Some of these are big. That one looks very big, but not quite as big as the Tarantula Nebula. And you can see the different colors of stars, which indicate roughly how old they are. The blue stars are very young stars. They've just been made. Yellowish stars are much older and have been around a little while longer, just like the sun. Messier 61 is a lovely spiral galaxy. It's in the Virgo cluster. Again, you can see these are smaller galaxies. They may be genuinely small galaxies, but that one is probably one further away, a galaxy in the distance behind the Virgo cluster. As we move on, here's another one. This is M90 Messier 90, another lovely spiral galaxy. But what you might notice here is that although it has the dust lanes and it has some hot white and blue stars, it doesn't have all of those big pink regions, these new forming star regions that we saw in the previous spiral and we see in our own galaxy. It's as if somebody's turned off the star formation. And this is a consequence of being stuck in a cluster of galaxies. If you're out in the suburbs, it's fine. You, as a spiral galaxy, you make stars to your heart's content. When you're surrounded by all these giant galaxies, they tend to strip away some of the gas that you have. The radiation from these giant galaxies or the gravity from these galaxies actually cause you to lose the gas that you use to make new stars. As you move through this cluster, although it looks as though there's nothing between the galaxies, there's a lot of gas there. And as you get pulled towards a big galaxy, you get all of your gas stripped away, and it shuts down the star formation. So poor old M90 has lost a lot of its raw materials to make new stars. Here's a collection of stars. This is called Marcarian's chain, and this is something we saw earlier, but now we can have a look at this chain of galaxies, and you can see it's all of these galaxies lined up from the bottom right to the upper left are all gravitationally interacting with each other. They're all part of the Virgo cluster. Named after Benjamin Marcarian. He was an Armenian astronomer who also was looking at a lot of these galaxies and actually was interested in finding galaxies with black holes in them. But he had this chain of galaxies named after him. If we look at some of them that are going to be interesting to us, we'll label them. M86, Messier 86, we know what that means now. There's one called the Eyes, which is much more interesting than M86. And then there's another galaxy just above M86 called NGC 4402, which is even more unappealing than M86. NGC stands for New General Catalog, a very, very sort of boring term of a list of galaxies and other objects in the universe that was made 100 or so years ago. And this is the 4,402nd object in that catalog, NGC 4402. So let's have a look at a couple of these galaxies because it's quite interesting to see what's happening. We talked a little bit about the two previous spirals. One was fine and doing its own thing. The other one, because of the interaction and the motion through the cluster being so close to all these galaxies, has messed up its star formation a bit. M86, Messier 86, is a third type of galaxy that we're going to come across. The first ones are spirals. Lovely spiral galaxies like the Milky Way. Second one are irregular galaxies, which by their name suggests they have not much shape at all. And they're usually messed up for some reason, usually gravity. And the third type of galaxy is this. It's an elliptical galaxy because it's elliptical in shape. Some of them are sort of spherical, like softballs. Some of them are elongated, like footballs or rugby balls. they're not flat. They're like spirals. They're actually sort of have a three-dimensional shape. And they tend to be the biggest galaxies in galaxy clusters, and M86 is one of the biggest. What you'll notice, first of all, is it's incredibly boring. There are no dust lanes, there are no star-forming regions, there are no disks. The only disk I see in this image is this little strip down here in the bottom left, which is actually a background galaxy that we can see through. But this fuzzy white thing in the center is basically a ball of 200, 300 billion stars. Now, there's no new stars being made. It's sort of fossilized in time. There's no gas to make new stars. And so it's just sitting there living out its life without making any new stars. And this is typical of elliptical galaxies. In some ways, some process in galaxy evolution, this galaxy has either used up or has lost all of its star-forming materials to make itself a big ball. It's a big ball of stars, and it's a big ball of gravity, because next door to it, we have a couple of other galaxies. These are called the eyes galaxies because there's two of them. Their proper name is NGC 4438 and NGC 4435, but we'll call them the eyes galaxies because that's cooler. The bottom right one doesn't seem to have many stars at all. It seems to be looks like a very flattened elliptical galaxy. These are called lenticular galaxies because they look like lenses. If you have a lens in your eye or just a lens in a magnifying glass, they're very sort of boring, again, like elliptical galaxies, just stars. The top galaxy, 4438, has all the characteristics of a spiral galaxy. It has the dust lanes, it has the nucleus that looks sort of yellowy, and it has the big blue big blue regions of hotter stars. But it is a mess, and it is a mess because of all of the other galaxies around it. This is a spiral galaxy that has really suffered badly from being so close to M86, and the gravitational tides are just basically destroying it, and may well ultimately absorb this material into the bigger M86 galaxy to make an even bigger galaxy. A similar story is happening with the little one above. This is NGC 4402. This looks like an edge-on spiral, but you can see it's bowed, it's bent, and what's happening is it is falling towards M86, and as it falls towards M86, the gas in the space between the two galaxies is pushing it. It's like you can imagine this is a skydiver just jumped out of a plane, and you can see his or her hair being pushed back as they rush towards the ground. And it's the same thing that's happening with this galaxy, is as it rushes towards M86 at hundreds of kilometers per second, it is being stripped of its gas, and it's being distorted, and it's being completely sort of messed up. And again, this is heading towards M86 and not going to do very well. It will eventually merge with the larger elliptical galaxy there. Lots of other wonderful things as we zoom around. I mean, if there's 2,000 galaxies, we could be here all night. But let's just look at this one, which is called the butterfly galaxies, because they look like the wings of a butterfly. In fact, here we have two spirals that are in the process of colliding, just like the Milky Way and the Andromeda Galaxy will in 4 billion years' time. The trouble is, if you're in a cluster of galaxies like Virgo, you are very, very close to other galaxies, and you have a lot of mass and they have a lot of mass, and galaxies tend to run into each other. And so they're either being ripped to pieces or smashing into each other, which sounds horrible, but the result are these beautiful dances of galaxies moving around. And even though things are moving so fast, hundreds of kilometers, hundreds of miles every second, these galaxies are shooting through space. And yet the scales that we're looking at here, each one of these galaxies is 100,000 light years across, containing 100 billion stars. The amount that they will move in a human lifetime is so small that you can't actually see anything change. You can come back in 10 million years' time and things will look very, very similar. But these are two other galaxies that are colliding, the lovely butterfly galaxies. And as they collide, they make new stars. And so you're going through this life cycle of star birth and then star death. So I realize that our cruise time is getting on. So I think we need to go to the star of the show and go to the center of the Virgo cluster as far as we're concerned, and the most important galaxy there. And this is Messier 87. Doesn't sound very impressive out of 104. It just happened to be the number 87th. It's a giant blob. It's an elliptical galaxy. And what you see there is not much detail, but let's look slightly closer at what's going on here. First of all, there is the elliptical galaxy, and it looks as though it's surrounded by stars. But those aren't stars, those are globular clusters. Each one of those dots is like Messier 4, the globular clusters surrounding the Milky Way, with hundreds of thousands or millions of stars in them. So each one of these dots is a million stars. And Milky Way has about 120 globular clusters. Messier 87 has 12,000 globular clusters. This is the biggest, pretty much, galaxy in our local universe. It has about 1 trillion stars in it, and is really the gravitational big gorilla in the room as far as the Virgo cluster is concerned. There's some other things going on. There's a couple of distant galaxies here that we can see, but if you look closely, and we're going to zoom in a second, there's a line coming out from the center of the galaxy. It looks like it's been shot by an arrow or something. This streak of light coming out of the center of the galaxy gives out a ton of radio waves. Messier 87, also known as Virgo A, the brightest source of radio waves in the Virgo cluster. So something weird is happening to this biggest galaxy. Let's get a bit closer. Here, as we move in, you can see a lot of these dots, and again, those dots are mostly globular clusters. The fuzz that you see are stars, part of the trillions of stars. Very, very little dust is such a characteristic of spiral galaxies, except in the center, you can see a few little bits of dust lanes. And then this bright blue streak shooting from the center. This streak here is about 4,000 or 5,000 light years long. Now, the width of it is roughly 10, 20 light years. And if you think the closest star to the sun, Alpha Centauri, is only 4 light years away, you get a sense of scale of this huge, huge galaxy and this strange jet that's coming out of it. And what we've got here is something, that's the astronomical equivalent of the Death Star. Because if we get closer, what we find is that this jet is made up of subatomic particles, electrons, maybe some other more exotic particles, being shot out from the center of M87 at almost the speed of light. So this jet traveling at hundreds of thousands of miles per second is being shot out from the center of this galaxy. And it appears to be coming from the very, very center of the galaxy. You really wouldn't want to be in the way of this jet as it comes out. The amount of radiation here would strip the atmosphere from your planet in an instant. So this really is nature's equivalent of the Death Star and the death ray that came from that. Let's get a bit closer. We don't want to go too close to the jet, obviously, because that's not a good idea. This is I have faith in the engineering of the spacecraft, but we don't want to get too close. So let's head to the very center, the very core of this biggest of galaxies. And when we get down there, as we get closer and closer, you can see the jet here. And the very center, again, is very, very bright with these streaks of a little bit of gas and dust surrounding the very, very core of this galaxy, surrounding the very center, a few hundreds of light years at this galaxy that's 100,000, 200,000 light years across. What's going on? Well, the same as all the other galaxies, including the Milky Way. At the very center of M87 is a black hole, but not just any black hole. This is just about the biggest black hole known. We said that if you were on the trip last time that the Milky Way's central black hole is a few million times the mass of the sun. This is billions of suns worth of mass crammed into a tiny volume of space, such that the gravity of that mass in that space means that light cannot escape, and you create this black hole. But surrounding the black hole is material falling into the black hole. And as this material, this is hydrogen, which is broken up into protons and electrons, which are charged particles, as they spiral in at 1,000 kilometers per second, as it spirals into this black hole and out of existence, generate these very, very strong magnetic fields. And those strong magnetic fields, sort of like sunspots, get all of the charged particles, and instead of falling into the black hole, it's shot out of the black hole in these jets. And this makes a wonderful paradox, the fact that a black hole is both the darkest object in the universe, and it's also the brightest object in the universe, from this ability to take some of the material that's falling in and shoot it back out. As we get closer in, we can see the ring of dust around the black hole, and in the center of the black hole, we can see darkness, or the center of the region around the ring. This is not actually the full black hole. This is the dark area. It's the shadow of the black hole over the dust ring that's incredibly hot as that material falls into the black hole. And to give you an idea of scale, the orbit of Pluto, which is the furthest, well, not a planet anymore, I'd like to think of it as a planet. The orbit of Pluto is 40 times bigger than the orbit of the Earth going around the sun. So you could fit the entire solar system within the O of orbit. So the O of the orbit is the orbit of Pluto on that scale. And the black hole is a few times larger than that. And you can see the ring of gas that falls in is larger still. This is an incredibly powerful, bright object. It's the biggest black hole known. The galaxy is just about the biggest galaxy known. And that makes M87, despite the fact it's just M87, the object. If aliens wanted to travel the universe and you're looking for the biggest and the best, you send them to M87. Let's get an idea of the map now. Here's the map of that galaxy, because we have to head back home. Here is a view of our local group, which is right at the center of this map. And there are some galaxies that we haven't had time to visit, maybe next time. And the Virgo Cluster, this huge cluster of galaxies away. And the distance from the center of this diagram to the center of the cluster is 54 million light years. That means we're looking at a map of our universe that is about 120 million light years across. It would take 120 million years for light to travel from one side of this diagram to the other. The Virgo cluster, as we saw, had a couple of thousand galaxies. Us, as well as the Virgo cluster, and all of these other galaxy clusters and small galaxies that scatter around thousands of galaxies, is what's called the Virgo supercluster. And it's all gravitationally bound together. And so we are part of the Virgo cluster, and we should be very, very proud of that. We're a long way from home. It's getting on a bit. So let's take a look back towards home. And as we turn our attention to where we came from, here we have a lovely view of the Milky Way and the Andromeda Galaxy, way out in the furthest reaches of the Virgo supercluster, 54 million light years away. That's a long way home. The Milky Way and Andromeda, as I said, they're part of the supercluster. They are being pulled through gravity towards the Virgo cluster. We're falling into the Virgo cluster. And yet, this raises something that's very, very interesting. Maybe more weird than M87 and its Death Star jet. Because we look at the Milky Way and it's actually moving away from us at 3 million miles an hour. During this talk, the Milky Way has moved 3 million miles further away, but it's being pulled into the Virgo cluster. How can it be pulled into the Virgo cluster and yet it's moving further away? This is something that is very, very bizarre. And what's bizarre, of course, is that our universe is expanding. We live in an expanding universe. And even though we are gravitationally being attracted to all of the galaxies in the Virgo cluster, the space between us and the Virgo cluster is getting bigger. Space itself is expanding, and as space itself increases in size, it carries the galaxies that should be moving towards each other away from each other. Unless you're very close. The space between Andromeda and the Milky Way is also getting bigger, but they're close enough that their mutual gravity is actually going to overcome that expansion of space. But the Virgo cluster is far enough away that even though we're falling towards it through gravity, space is getting bigger all the time. And so in the end, maybe gravity doesn't win out after all. But we need to get home because home is moving further and further away all the time. So let's head back to our galaxy. Here's the lovely Milky Way. It's great to see home appear over the horizon, and there's Andromeda in the background. And we're going to dive back into the disk of the Milky Way to get a familiar view. You can see now we've come back in the large and small Magellanic clouds to the top left. Lovely, lots of stars. There's the lovely dust lanes that elliptical galaxies don't have. And as we come to the end of our journey to the Virgo cluster and back, we can see a very, very familiar sight emerging. And we're back home. So to end that, thank you very much for joining me on this tour and this evening trip to the Virgo cluster.
That was amazing. Very beautiful. We went through a lot of places without getting hurt.
I was very relieved. I know. Take out good insurance.
Beautiful images as well. And to clarify, are those images that you showed us, are those actual telescope images?
They are, and of course, as we tried to pretend we were on a tour, I couldn't say that these were taken by telescopes. I think there were two, apart from the figures and diagrams, there were two artists' renderings. Everything else, images mostly by the Hubble Space Telescope, also by what's called the European Southern Observatory, which is down in Chile, that have very large ground-based telescopes. And all of these images are actually available from Astronomy Picture of the Day is the main source of these images, or you can go to Hubble site, which is the Hubble Space Telescope site for images. And all of these are available to see.
Wonderful. They're very beautiful images. It's just breathtaking. Well, we had a few questions that did come in. I think we have a little bit of time to take some questions.
Sure.
One question that came in was, are black holes a necessity for the center of galaxies? Do we see them in every galaxy?
Yes. Whether they're a necessity or not, that's a very good question. Like the sort of the seeds in the center of an apple. There seems to be black holes always seem to be present, and there seems to be a relationship between the size of the nuclei of galaxies and the size of the black holes. There's a very sort of tight correlation, even though black holes themselves are tiny compared to the galaxies surrounding them. It seems that, yes, pretty much every galaxy, there are a couple that central black holes have not been discovered, but these are the exceptions rather than the rule. Pretty much, yes, every galaxy has a giant black hole at its center. why is not clear. Whether, you know, and it's the chicken and egg. Did the galaxies come first and then make giant black holes, or did the black holes form? Obviously, they have a very, very high gravitational field and could act as sort of the nucleation site, if you like, for galaxies to grow. It's not quite clear evolutionarily. We need to look way back in time to see what's happening there.
All right. And in terms of stars and the age of stars, how do you interpret their age from temperature? And is a white star older than a yellow star? Which is older?
That's a very good question, and measuring stellar ages is something that astronomers have done very, very well. And if you look at a yellow star and a white star, you can't just tell that they're different ages, because they get formed at the same time. You get a star forming region like the Tarantula Nebula or the Orion Nebula close to us. It's forming high mass stars, which tend to be hotter and bluer, and low mass stars, which are yellow, and then all the way down to red stars. You need more information to actually tell how old those stars are. So if you just take a yellow star and a white star, you don't know that they could have been born at the same time. But one thing that we do know is that yellow stars last much longer than white stars. The hottest stars only last about 1-2 million years, 10 million years before they've used up their nuclear fuel, and then they explode and spread the nice elements they've made through the universe, and that's good because that's what we're made of. Yellow stars last much longer. They burn their fuel, even they've got less, they burn it slower, and they're around for 10-ish billion years. And then red stars last for a very, very long time. So some red dwarf stars, the lowest mass, are around for ages. So all you can tell just by looking is that if you see white stars, you know they are very young. You can't tell instantly from red stars or yellow stars how old they are. You need more information by looking at them in more detail.
Great, that's really interesting information. And what is the energy source for star creation?
Gravity. It's all down to gravity. So as we saw in the Large Magellanic Cloud and some of those spirals, you have a lot of raw materials for stars, which is hydrogen gas mainly. There's a hydrogen helium that was made in the Big Bang. And then you have other raw materials that have been created through generations of stars, like the dust that you see that block out the light of the stars. And that's made of carbon and silicon, very basic elements. And these clouds will collapse under the force of gravity. Sometimes that collapse is triggered by another star exploding, but what you need to do is basically push this material together. And if you squeeze it, it actually, gravity takes over, and then those gas clouds collapse. And as they collapse, they get hotter and hotter and hotter until you reach a point, the center of them gets so hot that nuclear fusion starts. And that's when the hydrogen fuses into helium and the star ignites. And then the collapse stops because now you've got the heat. And so you reach this balance point between gravity collapsing and heat from the nuclear reaction burning. And that gives you that lovely ball of gas that we see every morning, most mornings, is this balance between gravity and nuclear reactions. And that balance in stars like the sun, can last a long time, and that's good for life. It doesn't last that long for the bright white stars because they use up their fuel. They're partying, so they just use up their fuel, and then gravity wins, and they collapse and explode. But yeah, it's gravity doing it.
And so, do we know where the center of the universe is?
Well, that's a good quick question, because we are the center of the universe. So some people would say that's a bit of an ego trip. And aliens living in the Andromeda Galaxy would say they were the center, and not there's probably much living in M87, but if you were there, you'd say you're at the center, because from where you stand, it appears that everything else, as the universe expands, is moving away from you. But this is just a relative thing. Wherever you're standing, everything is moving away from you, because the space between the stars, the space between the galaxies, is uniformly expanding. So So there is no center at all. We don't know how big the universe is. We can see a certain distance, but then we sort of run out of time because the universe isn't very old. But there is no actual center, and that's one of the sort of peculiarities of picturing yourself, because yes, we are at the center, so are you at the center, so is everybody else at the center, because everyone appears to be where everything else is moving away from, and that's an optical illusion.
Well, thank you so much. I think we might be out of time for questions, but thank you very much for this wonderful, informative talk. You really do describe things in a way that is easy to understand, and we got a lot of great comments about that. So thank you so much for your
pleasure. Lovely. And have a good night, everybody. Thank you very much. This collaboration between the SETI Institute and Chabot, both non-profit organizations struggling to survive in these difficult times. But thank you very much for joining us, and we look forward to seeing everyone again soon.
Yes, thank you so much. And thank you so much, Dr. Steele, for taking the time to be with us today. And as you mentioned, please consider making a donation to the SETI Institute at SETI.org and to Chabot Space and Science Center at ChabotSpace.org. We would really appreciate it. And thank you all so much for tuning in. Have a wonderful evening and see you next time.